Right. Hello, everyone. Today is March 2nd. This is working group batch biweekly meeting. As you all know, this meeting is recorded and will be uploaded to YouTube. Please adhere to Kubernetes code of conduct during today's discussion. So today we have Paulo. He'll be speaking about data pipelines on Kubernetes with Kubeflow. Take it away, Paulo. Can you present?
Thank you very much. Yeah, thank you for inviting. Very happy to present this work into this community. And also, yeah, I'm working on Kubernetes quite a lot of time, so quite exciting to see.
Can you present full view?
Pardon?
Can you present or you just like the
yeah, of course. Yeah, I'm Paulo Di Tommaso. I'm the engineer at Creator Nextflow project. I'm mainly a software engineer. Currently, I'm CTO and co-founder of Secure Labs. That is the company that is maintaining Nextflow, the technology, but also the ecosystem tools around this technology. And okay, I think I can start by giving a brief overview of what is Nextflow, how we use into Kubernetes, what are our what's the value on Nextflow, how we use into this we Kubernetes cluster. So plenty of workflow engine for data analysis pipelines. So one I think can be interesting to focus why at least what is good Nextflow, why there is this adoption. There's quite a lot of usage into genomics data pipelines, also in other fields, but in most of the fields where there is a similar pattern. Essentially, Nextflow some I don't know is managed to handle very large data workload, and essentially the main problem that is focused the tool is to allow the composition existing script and research tool into a big pipeline. And also the very common problem with this kind of pipeline, they need to carry out computation on very large data set. So this is maybe something different. Other data pipelines that are so machine learning pipeline maybe are data intensive, but not very data intensive. Instead, this kind of data analysis, they need to really process a lot of data. We're talking about, I don't know, magnitude 500 terabyte for an average pipeline, and with a large number of jobs. There can be some hundreds, so 100 or 1,000. And the most typical way to handle the scalability in this pipeline is just to use an embarrassing parallelization model, or what is called perfect parallelization. Essentially, you just replicate the same flow over different data. And why people use this approach? Because most of these pipelines came out from research field, and these people, most of the time, what they need to do is just quick prototype data pipelines to validate an idea, and they put together a prototype, and then maybe it's working, and then this, in some extent, become a production pipeline. So, but the main goal to have a quick way to prototype the pipeline, put it together in existing tools. So these are some advantage. At the same time, the disadvantage of this is that this creates quite complex piece of software that are very difficult to maintain. They tend to be fragile. They have complex graph dependencies. So just to give you an idea, pipeline can be something like this. This is a companion parasite genome annotation pipeline, but here, okay, I don't want to enter into the logic of the pipeline itself, but it's interesting to see anyhow the complexity. We are not talking about 4 or 5 tasks, but really several dozen of tasks, sometimes 100 tasks. And each circle, of course, represents a task. And what is interesting is that there is a different piece of software that carry out the computation. So in other stack, in other data analysis tools, I don't know if I think Spark or something else, or other Airflow, this environment, they have an homogeneous programming language in which all the pipeline is implemented. And this is not possible in this field because, like I was telling you before, here the real problem to put together, compose this pipeline with research software tools that be implemented by independent parts. So here the real problem is to keep together all these tools and make scalable into a big cluster or computing cluster. And so the main challenge that we have in this context is scalability parallelization to carry out in a quick manner the computation, but also enable portability because also the same reason. These are maybe different researchers that work different institution, organization. Each of them can be used different cloud, on-prem cluster, or even single machine. So the problem is to make it portable the pipeline without having to reinvent every time. At the same time, guarantee reproducibility on this data analysis workflow that is not so obvious because when you have so many dependencies, it's very easy that you introduce subtle differences in your pipeline, you get different results. And this is what the context in which Nextflow has been designed and is mostly used. So I think these are the main areas somehow into this framework. The ability to write the pipeline code reusing existing piece of software by composition and the clarity manner you can create the pipeline definition, and then give a framework, give a the possibility to define also the prioritization of the pipeline, the clarity manner, so that who write the code, who write the pipeline, does not have to spend too much time low-level prioritization problem that can be quite complex if are not approached in the right manner. And the other important aspect of the tool is to isolate the dependencies with container, because like I was telling you before, each job can use different tools. Each of these is a different story to configure, to set up, to deploy in the system. So when you have those different tools and you need to deploy in a big cluster, you need to replicate the configuration in a single machine is a nightmare. Then with the idea of the container, you can just isolate all the dependencies into container and ship along with the pipeline. The difference with other applications, like can be any other service that use container, is that this pipeline can use many different containers. So this is another complexity that there is that can change over time for this certain reason. Since this pipeline change quickly because by the fact that this research tool change continues over time, then it continues to change this container. So it's quite complex to keep together all these pieces. And the other problem is to make it possible, like I was telling you before, to deploy, I won't say everywhere, so in some extent, there can be a single computer, different cloud, on-prem cluster engine, like Green Engines, LARP, LSF, Tor, there are plenty of this technology. And then, of course, Kubernetes, that is a leading technology, cloud container orchestration. Finally, is open source piece of software. You can download and use for free and contribute to it. And another nice concept that we add into Nextflow, the built-in integration with Git and GitHub repository. Why? Because this way, when you launch pipeline, essentially you are launching a piece of code that is on GitHub. The beauty of the tool that use all the Git tags and Git branch, like the revision of the project. So just referencing a tag, you can switch the execution of the pipeline in a different version, pulling not just the code, but also the configuration of the pipeline. And with the configuration of the pipeline, you can pull also the container associated with the pipeline. So there is a way to keep track all the different pieces of data pipeline that can be deployed with Nextflow. And okay, here there's a basic example to give you an idea what is Nextflow. This is not Nextflow, actually. This is just a piece of bash scripting where some tools is dynamic tools, but I want just to highlight how these people write tasks into this pipeline. Tasks into this pipeline are just bash one-liner or more complex script that can use normal Linux command like O combined with other genomic tools. This can be something simple, more or less simple like this, or more complex. But the idea is that you have just to compose tasks like this in a bigger script. So what we do in Nextflow is just embed the script that we want to run the user into a process definition. Into process definition, that means in Nextflow idiom that task, the job that you want to run, in which you define the input, one file, many files, whatever. But the main point is that this way we declare the interface, how this task, this process interact with the external world, and the task need to be executed. So essentially, this is file that is expected to be provided to run this task. It's supposed to be this one. Then you declare what is supposed to be produced by the task execution. This file, or FASTQ file, is a genomic file format. And then here you can write whatever you want that can be executed by the hosting system. So this is the main idea of Nextflow. And then an Nextflow pipeline becomes just a composition, many these tasks that interact each other. And also to focus a bit more on the idea of the parallelization. So I have, in this case, one task, then I can define a workflow. And essentially, then I want to execute this task. And what I'm doing, I'm taking this file, I'm using the pipe to say, okay, I'm giving this file to this task and execute the task. And okay, you may think, but why I need all this code when I could have used just these 2 lines of bash to do the same thing? Yeah, because the idea of Nextflow is to enable the parallelization of the pipeline execution, and you can model the problem with a single file, and maybe then you want to repeat the same execution over many files, many input files. And Nextflow, you can do this in a declarative manner. You can say, okay, it's not the channel that is created, that is this logic queue that we have into Nextflow to bring the data from the input to the task. So instead of having just one file, I want to take all the files that match this pattern. This is just a way, but it's the one that gives better the idea of the parallelization. So in this case, each file matching this pattern will trigger parallel execution on the task. So this is the main concept that there is in Nextflow. This idea of the data flow programming model, in which you push the data and the data trigger the execution of the task. And this is the same thing represented with the C#. Yeah, some files, the files go through a channel, the channel span trigger execution independent task, and then each of them can trigger the execution downstream task. This is the core concept of the tool. And then container, that is another important aspect on Nextflow. Like I was telling you before, the idea on Nextflow, you give a script, Nextflow, the Nextflow runtime, launch the job execution, and then what happens, usually this job depends on the configuration, the installation of the tool that need to be run in the hosting system that are provided by the hosting system, by the cluster or the cloud environment. And then the idea, like I was mentioning, the idea is just to wrap each job into its own container, so all the dependencies can be delivered by the container, and then the container run in the hosting environment. So using this approach makes much simpler to deploy the execution on these data pipelines in different contexts, from on-prem cluster to Kubernetes. And essentially what we do with Kubernetes is very similar to this. Kubernetes becomes just the container orchestration to run this pipeline at scale. And so how Nextflow runs into Kubernetes? This is more or less the schema, the core idea, even though this is more a legacy approach that there is to run Nextflow, in which essentially the Nextflow main application, the driver application of the pipelines run into the Kubernetes cluster like a pod. This pulls the code from the GitHub repository of the pipeline with the configuration, and then this starts launching pipeline job. Each pipeline job is a Kubernetes pod or a Kubernetes job. Initially, Nextflow was launching a pod for each job. More recently, it's possible to use Kubernetes job for Nextflow job. It's a bit better. And then each job pull its own container that is defined by Kubernetes. So it's very simple data approach. Yes, there is a question.
Is this Nextflow driver per flow, or is this one for the entire cluster?
Is one for?
Is the Nextflow driver per flow or per cluster?
No, per flow, per pipeline. Each, actually, yes. Each pipeline is a Nextflow application because manage all the orchestration of the pipeline essentially, and then decide to launch the job independently. And so the schema is very simple. There is not, at the end, Nextflow per se does not have a real scheduler. It just synchronizing and determining the parallelization of the task, and then start submitting tasks to the underlying cluster. One very ugly part into this deployment, and then the need to have a persistent volume claim to allow Nextflow and tasks to share intermediate result, because each task produces something, and this piece of data, the output one task, need to become the input downstream task, and so on. And to share all the intermediate result across tasks, Nextflow use basically a shared file system or a shared storage, which the data, which task need to be collected and passed to the downstream task. In Kubernetes, Nextflow had in the past strong requirement to use a persistent volume read-write many so that all the pods are connected essentially in the same file system. This is possible, but add a lot of complexity into the deployment scenario because this kind of file system are quite complicated to be configured. Does not scale very well, in my opinion, because they are designed for static cluster topology instead, especially in the cloud. The topology is much more elastic, so scalability sometimes is not very good. They are quite expensive technology. There are some on the market that are very good, but are also very expensive. In any case, the problem is that you still create a lot of a bottleneck from the management point of view, because there is some guys that need to install this, need to maintain this file system. It adds a lot of friction from the operational point of view. And so this is my point is that this approach using shared file system, especially with Kubernetes, is an anti-pattern that we would like to avoid as much as possible. Ideally, what's the best solution? The best solution for cloud native pipeline is the ability to use just an object storage, because cheaper compared to a shared file system or other storage solution, scale in infinite manner, at least virtually. There's no extra configuration. You have just S3 bucket, cloud storage bucket, take the data right there, much better. What's the problem? The problem is that there is an API mismatch, because all these tools are written for POSIX file system, to read files and no local file system, are not written to ingest data from on object storage. Maybe it could be adapted, but out there is so many data science tools that are not written for the cloud that it's impossible to convert all of them, I don't know, to Amazon S3. And so this is the work that a point in which we worked hard recently in the past year with the idea. I know this is just to give an idea what is doing Nextflow or other tool when you use a bucket or S3 bucket for the execution. Maybe you have a container running into a EC2 instance. This can be a pod. In any case, this guy needs to take some input data from Amazon bucket, copy in the logout stretch disk, run the computation, this write some output here, and then you need copy out the result. So imagine this for millions of tasks. Every time you add a lot of time to take the data, compute, and write the result back, up and down, back and forth all the time. And so this is introduced a lot of great bottleneck pipeline execution. And to solve this, instead, we work hard implementing a better solution that we call Fusion File System that work natively in Nextflow. And when we deploy with Kubernetes, essentially Fusion File System is a Fuse driver. There are plenty of Fuse drivers out there, but this is a bit different because we mount the this Fuse driver within the container. So this allows us to optimize all the data transfer that this driver does, also because it's able to use the instance of the local disk, the local solid state disk when available, that make the data transfer much faster. And yes, so using this approach, we can manage to have very nice improvement on the performance. We made this nice benchmark showing how improve the capability to run a scale the pipeline. Essentially, we compare the same pipeline using just Amazon S3 and copy the data in the job, the container, and copy back the result like I showed you before, or using fully featured sharded file system like FSX for large tree. And this is the Fusion technology. So this has a big impact on the overall compute time. If you see, using a straight same pipeline needed to run 766 hours, in which 200 were only for data transfer, moving the data. So these are a lot of unnecessary expense to your data pipeline. Of course, last trade much faster. Indeed, there is no data transfer because you use the transfer system to read and write the result. So there is no need to copy, start, and copy back the result. But the interesting part is that using this approach that we have with Fusion is even faster than the last trade. Because at the end, S3 is very fast. If you manage to download your data in a parallel manner and manage to use in an efficient manner the local SSDs can be very fast. And then we managed to achieve basically the same result that you can have a sharded file system with the Fuse driver running into the container. And the cool part is that not only this approach is fast like a sharded file system, but it's much cheaper because basically we don't have to pay all the cost of the sharded file system, and the computation run much faster. So here we also managed to calculate how much it costs the execution of the same pipeline in three different technology. And essentially, you save a lot on the storage that you pay, because this column shows the cost for the single run. This basically include the cost of compute and cost of transfer for that execution of the pipeline. S3 FSX more or less the same. So here in reality, there is less cost for compute, but you pay more for the data transfer that is charged by the use of FSX. Instead using Fusion, the computation is much faster, but you don't have to pay the FSX data transfer. And instead, in this column, I'm showing the cost that you pay to keep the data in the storage for 1 month, because when you compute something, you don't throw away the result, but you keep there for some reason because you may need it in the future. And of course, FSX is much more expensive from S3. So this basically bring very, very interesting cost saving. And so this is quite interesting because essentially we remove the need to have a sharded file system when we deploy Nextflow into Kubernetes cluster, and still remain an interesting question. Okay, this is basically the same chart that was shown before, but using the new approach, essentially we can have Nextflow just spawn the job execution into the Kubernetes cluster. There is no need anymore. The shell file system can use leverage storage directly. And an interesting question is how we can run this fusion driver into the job container without rebuilding the container. Because principle to run this tool, there are many different ways that you can run piece of software within a container, or maybe using a daemon set, using a sidecar container, or mounting the binary client into the container. But all these solutions were not fitting well our need. And we ended up creating our own solution for this problem. So the problem is that we want to instrument the container. We want to run a piece of software within the container without rebuilding the container. And we further implemented this service that we call Will Container, that is essentially is a container provisioning service in which the pipeline is pulling the container directly from the registry, pull from the web service. The web service is essentially a proxy between the Docker client and the registry that is able to instrument the container and add a new layer. And the new layer contains some infrastructure tool that we want to use into the cluster. And so this is the main idea. How does it work? Imagine that you have Docker client, you want to pull a container. I guess more or less all of you know how does compose a Docker container into a manifest JSON file. The manifest of the container is a list or layer. And then when you ask the container, you are asking the manifest to the registry, and then the Docker client pull all the layer one by one that are tar file. And what the web service is doing is just sitting in the middle, intercept the request, and when you ask the manifest, that is the configuration plus the layer, we are adding just a new layer on the fly. And this allows basically to transform a request of the original container to the same request with the Fusion client added into the container on demand. Just to give you an idea, how does it work? Otherwise, I have too many words. Imagine that I want to run through the very small pipeline. This is a pipeline that is hosted into a GitHub repository. Just to, like I was telling you before, Nextflow pipeline is a GitHub project in which there are some code, the pipeline they want to run. This is the main execution, the small pipeline, but this is not the important thing. Important thing is that, okay, I want to run this into Kubernetes cluster. The configuration is not very complicated. Essentially, there is the setting up part of the usual thing, the namespace, the service account, which there is the binding with the Amazon service account. They give it the permission to access the bucket where the data is. Some minimal permission to run the pod, get the pod, is kind of stuff, and then the role binding. So nothing special. This is the AWS permission to access this bucket where there is the stuff that we want to, where we want to write the data, read the data. Okay, this is the trust relationship with these Amazon details. And this is the Nextflow configuration. Also here, there is not much stuff to say. The context, that is the cluster I want to use, namespace, the service account. Okay, and then I have cluster running here. Let's say I want to do key, just an alias from kubectl and get the pods. Now there is anything. And then maybe I could do cut run. I think it's just a Nextflow run RNSig. Essentially, I want to run this. This pull the code and launch the pipeline into the remote cluster. So you jump into the pipeline. You see, start launching the pod and running the corresponding jobs as pod here into this. Oh, okay, it's quite fast. A few jobs I finished quite immediately. And so this is, I think it's quite interesting because this pipeline run my computer and the the execution, a remote cluster, and the two talk basically share the data using the S3 bucket, using this S3 bucket that is configured in Nextflow configuration. So this one, which there are all the intermediate results essentially. No, AWS S3. Okay. So these are the main things I wanted to show. I'm sorry I didn't talk much about scheduling and queuing into Kubernetes, but already there are very little into Nextflow specific for this at this time. Surely future work that we want to look into Nextflow to follow more the batch specification, the work on which we are working. I think can be very interesting to extend the possibility of the tool. We feel that before we had to solve this problem of the storage into Nextflow, Kubernetes was really a blocking point. But now I think it can be very interesting to how to improve the scheduling capability and the queuing capability on Nextflow with Kubernetes. Another interesting project that I think can be interesting to mention in this context, I think you should try to have a chat with this guy. This initiative they called Common Workflow Scheduling Interface. Here the data that is developed by this guy, University of Berlin. They published a paper recently. The idea is to create a meta scheduler that sits between a workflow engine, can be Nextflow, SnakeMake, Airflow, whatever, and the target cluster that can be Kubernetes. And the idea of this workflow scheduler interface is that other than the job definition, receive also the task dependent, the job dependencies at the graph, the DAG of the job that need to be executed. So basically, this interface adds some intelligence to better control the scheduling to the underlying cluster.
Just a quick time check. We have 7 minutes, and just in case we have questions at the end.
Yeah, indeed. I just finished, so I want to say thank you. Yeah, exactly. If there is any question, happy to take.
I have one question, but I want to open the floor first to the community, if there are any questions.
I have one. So
yeah.
you said that you're migrating from pods to jobs, and you say it's much better. That's very good to hear. We've put a lot of effort on it. So can you share some general things that were helpful, and also if you have any other petitions for the job API?
What could be interesting from that point of view, workflow engine, especially at least the workload that we submit, we would like to be able to control, for example, things like instance type. That is, I know that is something does not match very well the job API in general, but there is more and more need to control the type of the instance when you submit a job. Also reference to the architecture, for example. Now there is some pressure to be able to deploy pipelines into, I don't know, Graviton architecture, or even have mixed deployment in which we have some jobs run on Intel, some jobs run on Graviton, some jobs run on GPU. So I mean, the job API that is able to specify which architecture you need for the job would be very useful.
But wouldn't that be possible with labels and affinity?
Possibly, even though there's still too much customization. I would say it would be nice to have something that, okay, I want to use ARM64, I don't have to create my own custom label that they work only on that specific cluster deployment, no?
Right. But that's the cluster autoscalers work. I mean, right?
I think the question here is kind of like we already have the capability, but there is no standard way of specifying
Yeah, exactly.
across different providers, right?
Yeah, maybe then, I don't know, because at the end you are working with a bash queuing system Kubernetes. Essentially, when you have queue, the queue allows you to define the hardware capability that you want by that queue. So maybe it's something that's implicit solved by the queue specification. But yeah, to tell the truth, I don't know much what's the status of batch specification.
Right. So it boils down to defining a common label, or maybe defining an intermediary, like in our case, Q, that injects affinities to specific, or like if you're working on AWS, then the name of that architecture is, or label is X, and the other one is Y. So you inject them on the fly, basically.
We actually have some form of this capability in Q with a K. So yeah, let's stay in touch to
Yeah, definitely very interesting. Yeah.
My question is more about, related to this, like queuing in general. Like, how do you think about workflows and queuing? What do you queue? Do you queue the steps? Do you queue the workflow? Like, did that come up in the past? Do you have integrations with existing queuing systems, even outside Kubernetes?
My experience with Nextflow, the queue is very important because yes, allows you to, what I was mentioning you before, to segregate the task execution from some specific hardware requirements. So I think having this also into Kubernetes would be quite powerful. At the end, in practical terms, from Nextflow point of view, is just simple declaration that we have in the task definition, which you say, I want to run this task into this queue. That's it. And then in the Nextflow configuration, we can associate to the queue some specific hardware requirement that is CPU memory for that specific task. But yeah, usually this is quite useful. Also because most of this workload came from legacy implementation that were running HPC batch scheduler like Slar, like Green Engine, in which there is this concept. So these people really love to move this pipeline from on-prem cluster, in which they have queue, to Kubernetes cluster, if possible, maintaining the same concept. So having something that can have the same model is very useful.
What does a queue govern here, like within Kubeflow? Like, and how does it interact with the queue in Slurm, for example, or if an external queuing system that manages the lower level infrastructure?
Didn't get very well the question. What guarantees?
No, what does it govern? Like the queue here that you have within Nextflow versus, for example, if you're deploying, my understanding is that you can deploy Nextflow on top of Slurm, right?
Yeah, indeed. Essentially, yeah.
And Slurm itself has also the queue concept, a queue concept and governing resources. So it's not quite clear to me how those two interact.
Well, essentially, what is doing here, we transform into this job into, in this case, some Green Engine, but can be slower, and then submit to the corresponding queue that there is in the system. Then the user can even specify some specific resources, number of CPU or memory, but need to match with the specification of the queue. Otherwise, if does not specify anything, inherit the default of the queue. So this is something that can be useful, that you just provide You say, okay, you have some queue in your pipeline. These are high mem queue, or this is high compute queue. And then without changing the parameterization in terms of CPU memory in the pipeline, you just submit this stuff to the cluster. Not sure if this answered the question.
Yeah, I mean, like you're using the queue to basically define the resource types that are assigned to the tasks, I guess. But does it actually enforce quota? Does it have like, you know, ordering guarantees? There's like multiple workflows from different tenants, different users. Can they share a queue, and what would the interaction be? Yeah, this is the way that I'm thinking about queue, more about like resource management between tenants potentially, and ordering. But I mean,
I don't know if you have a very specific question for this, but anyhow, the need that I see from people using this tool, that they need to segregate job execution different queue, and most of the time, for example, there are some queue that are shorter time constrained, so because they are supposed to run faster jobs. And sometimes maybe not very common, but what happens that they submit some jobs into a short fast queue, but then the job cannot complete because it takes longer. And so they want to switch the execution into another queue in which they are allowed to perform the computation for a longer time. But the main need is essentially, to segregate the tasks depending the hardware requirement or the resource requirement that there are for the tasks.
Okay. Any other questions? All right. Thank you so much, Paulo, for
Thanks a lot.
presenting.
Thanks a lot.
I'm going to stop the recording.
Thank
All
you.
right.
Goodbye.